let's explore the world of vertical asymptotes and holes in graphs. We have four rational functions here. Again, a rational function is just one where there is a variable in the denominator. So these are all rational functions. As we know just from our experience mathematically, when the denominator is 0, something is going to happen. Now, we need to determine whether that something is going to be a vertical asymptote or a hole. A vertical asymptote is an infinite discontinuity, whereas a hole in a graph is called a removable discontinuity. Let's explore how we can determine which is which based on the function, and then see how that relates to infinite limits. Let's take a look at the parent rational function 1 over x. We can see here that when x equals 0, clearly the denominator is 0. This one's pretty simple. Well, we end up having a vertical asymptote here, the vertical line x equals 0, because that is what makes the denominator 0, and there's nothing that cancels it in the numerator, so there's no hole in this graph. We'll kind of see what that means in just with this last example here. Let's see how this relates to limits and how we can write an infinite limit. We can clearly see that since 0 is kind of our problem area, we can say that the limit as x approaches 0 does not exist for this function 1 over x. We see that because the overall limit just doesn't exist here. However, the one-sided limits do. Let's explore as we approach 0 from the left and approaching 0 from the right. We can see that as we approach 0 from the left, the line x equals 0 here, our graph is going down, 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 down to negative infinity. As we approach the vertical line x equals 0 from the right, we can see that our function goes up, up, up towards positive infinity. Here's how we can write that. We can write the one-sided limits just like this. As we approach 0 from the left, our function, it's negative infinity. As we approach 0 from the right, we approach positive infinity. Therefore, the overall limit, again, one without a little negative or plus symbol here, we would say does not exist, since the one-sided limits are not the same, and also they're not even a number. So it's okay to have one-sided limits equal the infinities, but it is not okay to have an overall limit equal infinity. We would then say it does not exist. Let's take a look at our next function. This one I'm not going to spend too much time on. They're both graphed now. So if we look at the blue function, we can clearly see that the number that would make the denominator 0 here is 1. So we do actually have a vertical asymptote at x equals 1 here. So it's just the parent rational graph shifted 1 unit right. Then if we take a look at the next function, let's see how we would have two vertical asymptotes for this function. If you think about this next rational function here in an algebraic way, we can clearly see that there are two numbers down here that would make the denominator 0. Those two numbers are 3 and negative 3, since when we square them, we'll get 9. 9 minus 9 would make our denominator 0. Nothing, again, cancels in the numerator. Again, we'll see that in the next example. Therefore, negative 3 and 3 are both the vertical asymptotes of this function. Let's see how we can write those with limits. I've sketched the vertical asymptote x equals negative 3 right here, and I've written both the one-sided limits. As we approach negative 3 from the left, we can see that our limit is infinity. As we approach negative 3 from the right side, we can see that our limit is negative infinity. Therefore, the overall limit as we approach negative 3 does not exist. This is x equals negative 3 is an infinite discontinuity. I've also written out this function in factored form, so we could clearly see that 3 and negative 3 are the two vertical asymptotes. We could also analyze the other vertical asymptote, x equals 3, in the same manner. It would actually just be swapped from the left and the right side. This last rational function looks a little bit different. We can see here that our numerator is different, but the denominator is the same as the previous one. Let's write this one out in factored form just like we did earlier. We see here that we have the difference of squares now factored in the denominator, but our numerator also has a common factor with the denominator, that x minus 3. So what happens is that we can actually cancel out the x minus 3's. This function in simplified form is 1 over x plus 3. However, we cannot simply just forget about the fact that 3 also makes the denominator 0. So I will simply write that x can just not equal 3 in this case. Now, what's occurring there, we'll take a look at in just a moment. With this simplified version of our function, we see that it's now a more simplified rational function, and negative 3 makes the denominator 0. That factor, x plus 3, did not cancel at all. That is why it didn't cancel. X equals negative 3 is still a vertical asymptote. However, the factor that did cancel was x minus 3. What made that 0 was 3. When x equals 3, we still have an issue, although it's not a vertical asymptote over here. What is occurring here? Well, we can't see it, but there really is a very, very small hole, a removable discontinuity, where x equals 3, down here. We cannot see it on the graph because it is so small. However, we can see it using a table. Let's take a look. Looking at this table, we see that when x is 3, we're clearly undefined. It is difficult to see on here, but there is a very small hole right there. So this function, this rational function right here that we started with, has two discontinuities, one at 3 and one at negative 3. At negative 3, we have an infinite discontinuity, which is a vertical asymptote. At 3, we have a removable discontinuity, which is a hole. We understand that algebraically, that when we factor, and when we have a factor that cancels top to bottom, that turns out to be a hole. I think about it as, look how easy this was to remove. It's a removable discontinuity here. Let's write that out. Here's how we can write this out using some calculus verbiage. At x equals negative 3, we have a vertical asymptote, which is an infinite discontinuity, and at x equals 3, we have a removable discontinuity, which is called a hole. We saw in the previous examples on Desmos that we can also talk about vertical asymptotes as x approaches that whatever x value from the right and from the left, if it goes to one of the infinities, we clearly have a vertical asymptote there because the function is darting way up high or way down low around that value, and it is a vertical asymptote. So this is the official definition of a vertical asymptote. It's also online in your book, and if you want to write it down, we do use limits to talk about vertical asymptotes. In this example, we want to find the vertical asymptotes for each graph, and then describe the behavior to the left and the right of each vertical asymptote. I actually have two parts here. It does f of x here, but I have f of x and g of x for each. Let's take a look at the first function. Go ahead and factor that first. Once we factor the difference of squares, we can see that we're going to have discontinuities wherever the denominator is 0, which would be at negative 2 and 2. And in that case, we have to determine which one of those, if any, are vertical asymptotes. Well, does anything cancel top to bottom? No. There's only a 1 up here. There's not the same factor top to bottom. So since nothing cancels, both of these are vertical asymptotes. They're both infinite discontinuities. So we have vertical asymptotes at x equals negative 2 and 2. Now, in order to determine our one-sided limits at each vertical asymptote, you can definitely just use a graph. I recommend that just because I think it's easiest visually to take a look at it. So let's do that. Here's a super rough sketch of the graph, and we can see that we have the two vertical asymptotes there at negative 2 and 2. So let's write out the one-sided limits. Here are the 4 one-sided limits. Again, we have 2 one-sided limits for each vertical asymptote, one from the left and one from the right. So go ahead and pause the video and see what you get for these 4 one-sided limits. Here we have our 4 one-sided limits for these 2 vertical asymptotes. Let's take a look at part B. Go ahead and factor g of x and then determine where we have certain discontinuities. We want to classify each discontinuity as either removable, a hole, or infinite, a vertical asymptote. So pause the video and factor g of x. Okay, we have factored g of x. We can clearly see that there are going to be 2 discontinuities once again, since the denominator is actually the same as over here. And again, discontinuities are going to occur where the denominator is 0. And so here we have at x equals 2 and negative 2 once again. However, we can see that x minus 2 actually cancels. It's a factor that cancels top to bottom. So let's classify each one of those discontinuities. Because x minus 2 cancels, the x value of 2, the one that made it 0, is actually a hole. It's a removable discontinuity. Because x plus 2 did not cancel, the number, -2, that made it 0, is an infinite discontinuity, which is a vertical asymptote. Let's take a look at writing the limits around our vertical asymptote x equals -2. And then let's also explore the limit as x approaches 2. Here we can see what a really rough sketch of this graph looks like. Let's take a look at the one-sided limits around x equals -2. So go ahead and pause the video and write out both one-sided limits as x approaches -2 from the left and from the right. There are our two one-sided limits for our approaching our vertical asymptote x equals -2. Now our whole, we haven't really looked at this too much, but we have studied already how to find limits here with factoring and canceling. That is what we are going to do. Let's take a look at this here. We want the limit. We've already factored and canceled. The limit as x approaches 2 here of our function. Well, originally, if we plugged in 2, we would get 0 over 0, so indeterminate form. However, we have factored and canceled, and we were left with this once we've canceled out the x minus 2's. Now we can use direct substitution. When we do that and plug in 2, we'll have 8 over 2 plus 2, or 8 over 4, which is 2. A lot of 2's in this problem. That means that this coordinate point here, what would have been is 2, 2, but there's just a hole there. So our limit as we approach 2 from the left and from the right is both 2. And that is why if you do graph this on Desmos, it will just look like it flows straight through. But if you do look at the table, if you plug in 2, you will get undefined. However, the limit is 2 because that's the y value it approaches. And here's our second and last example in this video. Go ahead and pause the video, get these written down, and then go ahead and factor f of x. This one's a little bit more challenging. Remember how we can make this look like x minus 1 by factoring out a -1. Pause the video, see how you do. Here is the factored form of f of x and the work down here for the denominator if you need to take a look at it. Now, our next step is to see what makes our denominator equal 0. Well, there's going to be two values of x. Those values are going to be -1/2 and 3. If this one's harder for you to see, write out 2x plus 1 equals 0 and solve it. We'll get -1/2, and then that one is clearly 3. So we're going to have discontinuities there. Now, what type are they? Well, do any of our factors cancel? No. So because none of our factors cancel, both of these discontinuities down here at -1/2 and +3, they're both going to be infinite discontinuities and look like vertical asymptotes on our graph. This graph does not have any removable discontinuities. It only has the two infinite discontinuities. Graph this f of x into Desmos and go ahead and write out the 4 one-sided limits for 2 for each vertical asymptote. Pause the video and then play to check your work. Here are the 4 one-sided limits, 2 for each vertical asymptote. The overall limits at -1/2 and at 3 do not exist. In part B, we have our first trig function, and we know that tangent of x can be simply rewritten as sine over cosine, and so when we do that, we can see that there is in fact a denominator here. And so we're just looking for when cosine of x equals 0. The cosine of x equals 0 at an infinite amount of x values. The first one, if we think about our unit circle, is pi over 2. The next one is 3 pi over 2. I mean, we could keep going on and on. We could actually go in both directions. And so the way that we want to write this is simply starting at pi over 2, the smallest x value that's positive, and then think about what we're adding on every single time. We're adding on an entire pi. It's every 180 degrees or halfway around the unit circle. So the way that we can write that is plus k pi, where k is in fact an integer. So from here, describing the behavior, I'll just pick the first one since there are an infinite amount of vertical asymptotes, pi over 2 being one of them. I will pick that one. So we'll do the limit as x approaches pi over 2 of our function g of x from the left, and we'll find the limit as x approaches pi over 2 from the right of our function. Go ahead and find each one of these using either your memory of what the graph of tangent looks like or graphing it. Here are the two one-sided limits. I used just my memory of knowing what the graph of tangent looks like. However, if you need to use Desmos to graph it, that is totally fine. In this video, we talked about infinite limits, and we talked about whether a discontinuity of some sort of rational or trigonometric graph function was a vertical asymptote or a removable discontinuity. We did that using factoring and other techniques.